Dear students, in last class I have explained an important concept called electric flux. So, what is the definition of electric flux? Number of electric lines of force passing normally through a given surface is called as electric flux. Mathematically, we can measure electric flux through a small surface having area delta S in an electric field E is given by delta phi is equal to E delta S cos theta. E is electric field, delta S is area vector and theta is the angle between electric field and the area vector. What is the direction of the area vector? The direction of the area vector is always normal to the surface and then perpendicular. It is normal to the surface and perpendicular, and it is outward. So, keep that in mind. If you want to measure the total flux, the total electric flux through a given surface is given by phi is equal to summation E delta S cos theta. So, algebraically we add the flux through the entire surface and then we find the total flux. The flux is related to the field, field is related to the charge, and that relation between the flux and the charge is given by an important theorem called Gauss theorem, which states that the total electric flux through a closed imaginary surface in free space is equal to 1 by epsilon naught times the total charge enclosed by the closed surface. And based on this Gauss theorem, we have three important applications. There are many applications, but in our syllabus we are going to derive expression for electric field due to different shapes of the charge conductor. In that first one is expression for electric field at any point due to a charged spherical shell. Charged shell. So, shell means it is a hollow, it is a sphere. So, this is the sphere and it is a hollow. Since it is a charge, the charges are uniformly distributed over the surface like this. Charges are uniformly distributed. So, let capital R be the radius of this spherical shell. Capital R is the sphere. We want to find the electric field at any point. So, we are going to consider three cases. One, a point well outside, a point very close to the sphere, and then a point inside the sphere. And to apply Gauss theorem, we need a Gaussian surface, which is an imaginary surface enclosing the charge. So, I am going to consider a point P here, and passing through that point, I am going to assume a Gaussian sphere. So, imaginary, so it has to be dotted line. So, consider a Gaussian sphere. So, this is the Gaussian sphere. The point P here is on that sphere. And now that point P is at a distance r, small r. So, small r is the radius of the Gaussian sphere, or it is the distance of the point from the center of the sphere. So, I want to find the electric field at point P. To find the electric field, first I am going to assume a very small area here surrounding the point P. Consider a small area. What is the direction of the area vector here? The direction of the area vector is here like this. This is the direction of the area vector. Okay, this is the direction of the area vector. Since it is positively charged, the sphere is positively charged, right? So, therefore, the field is also in this direction. The field and the area vector both are along the same direction. So, one is a delta S vector because it is a normal to the area, right? The area is here, this is the area. So, normal to the area, normal to the surface area is delta S, and then vector E. It is outward because the charges are positive. If the charges are negative, then the field is inward towards the center. So, now let us find the flux through that small surface. So, the flux through that small surface is given by delta phi is equal to E delta S cos theta. Flux through that small surface, this area, small area. What is the theta? Theta is 0 because both the vectors are along the same direction. So, since the theta is 0, the flux is given by E delta S, cos 0 is 1. Now, electric field at this point or at any point on the sphere is same, because from the center every point on the Gaussian sphere is at equidistance. So, that means electric field is same at each and every point on the Gaussian surface. So, that is why now we can definitely measure the total electric flux is equal to summation of E delta S. Theta is always 0. So, that is E into, because E is same at each and every point, summation of delta S. That is equal to E into, what is sigma ds? Sigma ds means sum of the area. This is delta S. If I add such area, then I have to add the summation of the entire Gaussian surface. What is the summation of the entire Gaussian surface? Summation of the area. It is area of the sphere having radius small r. So, that is why the summation delta S is nothing but 4 pi r square. So, we have measured the flux using one of the equation. We can even measure the flux using the Gauss law. So, according to the Gauss law, the total electric flux through a closed imaginary surface in free space is equal to 1 by epsilon naught times what is the total charge enclosed. So, the total charge here I am going to consider it to be equal to Q. So, therefore, 1 by epsilon naught into Q. So, we have another equation for the flux. And now, we have to find we have to equate them, because this will give you the total flux, this also will give you total flux. So, therefore, equate E into 4 pi r square is equal to 1 by epsilon naught into Q. So, therefore, E is equal to 1 by 4 pi and this epsilon naught into this Q by this r square. So, this is one of the expression for electric field at a point outside a charged spherical conductor. So, this is one of the case. I am going to consider second case, that is I am going to shift the point P instead of well outside, consider very close to the sphere. When you shift the point very close to the sphere, then the value of r becomes almost equal to the radius of the sphere, isn't it? So, the second case, so this is the case number 1, and now in the second case, when the point is shifted, when the point P is very close to the surface, then the value of r is approximately equal to capital R. So, that is why we get expression for electric field E is equal to 1 by 4 pi epsilon naught Q by capital R square. So, this is the formula for electric field at a point close to the surface of a charged spherical shell. Understood? Case number 3, when the point is inside. If I take a point inside and then if I assume a Gaussian sphere, then you get to see that the charges are outside the sphere, they are not enclosed by the sphere. And when the charges are not enclosed, Q is 0. Therefore, the flux, when Q is 0 here, when Q is 0, even E is also, E becomes a 0, right? Or you can even consider like this, when Q is 0, flux is 0. Right? And when the flux is 0, what is the electric field? Electric field is also 0. So, this is the third case. So, the conclusion is that electric field anywhere inside a charged sphere, not only charged sphere, any charged conductor, the electric field is always 0. So, this is a one more question. So, what is the expression or what is the value of the electric field inside a charged conductor? It is always 0. So, we have 3 different cases. Electric field at any point well outside, okay, is given by 1 by 4 pi epsilon naught q by r square. At a point on the surface, E surface is 1 by 4 pi epsilon naught q by r square, and then at a point inside, the electric field is a 0. So, this question again is important. It has appeared almost 5 times in the examination, in the board exam. So, that is why this is an important derivation for 5 marks, okay, where they will ask derive an expression for electric field at any point due to a charged spherical shell. So, you have to draw 2 spheres, one the real conductor, this is a conductor, the other is imaginary, that is why you have to draw a dotted line only, dotted line, yeah, dotted, not line exactly, the dotted sphere or dotted circle as it appears on the board. So, hope we are clear with this particular derivation. So, 3 cases to be derived: at a point well outside, at a point on the surface, and at a point inside the sphere. So, based on this concept, so we have a numerical. First, let us solve that particular numerical. So, this derivation is one of the important derivation from the exam point of view. So, we have a numerical here. So, let us solve this numerical. Go through the statement. A spherical conductor of radius 12 centimeter. So, radius is given, radius capital R 12 centimeter, which is a 0.12 meter, conversion is a must. Has a charge of, so charge is given Q, it has a charge of 1.6 into 10 to the power minus 7 coulomb, distributed uniformly on its surface, that is the total charge. What is the electric field? Option A, inside the sphere. So, option A, E inside the sphere, we know it, we do not need any data for that, because electric field anywhere inside is always 0. Option number B, just outside the sphere. So, just outside the sphere is E is equal to 1 by 4 pi epsilon naught q by capital R square. 1 by 4 pi epsilon naught is 9 into 10 to the power 9. The value of the charge Q is 1.6 into 10 to the power minus 7 by the value of the radius capital R 12 centimeter or 0.12 square, correct. So, let us simplify this here, the value of the numerical. So, we have 9 into 1.6 divided by 0.12 square. So, that becomes 10 to the power 3, that is 1000, what we get. So, that is, let me check again. So, 9 into 1.6 divided by 0.12 divided by 0.12. Yes, so that is 10 to the power 3 into, so here we have power plus 9 and minus 7 is a plus 2, so 10 to the power 2. So, you will get 10 to the power 5 Newton per coulomb. Now, that is the value of the electric field just outside the sphere, or in simple, just outside means on the surface, that is the second formula that is to be used. Okay. The third one, option C, at a point 18 centimeter from the center of the sphere. So, the value of R is 18 centimeter, which is 0.18 meter. So, therefore, the value of the electric field is 1 by 4 pi epsilon naught, it is a q by r square, that is 9 into 10 to the power 9. The value of the q is 1.6 into 10 to the power minus 7 divided by r is 0.18. 0.18 square. So again let us simplify this. So that is 9 into 1.6 divided by 0.18 and further divided by 0.18. So we will get 444.4 into 10 to the power plus 2 here, 10 to the power plus 2, which we can even write like this. It's, if you shift the decimal here by 2 digit, you will get 4.444 into 10 to the power 4 Newton per coulomb. So that is the second option, option C. Let us see if there is any more. Okay, we have option D. What is option D? It is a surface density of charge. It is a spherical conductor. How to find the surface density of charge? So since surface density of charge sigma is equal to Q by 4 pi r square. The value of Q 1.6 into 10 to the power minus 7 divided by 4 divided by pi, which is 3.142, into the value of r radius, which is 0.12 the whole square. So again let me simplify this. It is 1.6 divided by 4 divided by 3.142 divided by 0.12 and again divided by 0.12. So we will get a value of 8.841 into 10 to the power minus 7. Now it is a charge is coulomb and square of the radius means meter square. So coulomb per meter square, coulomb per meter square. Okay. So there is one more option, option E, that is option E. Number of electrons lost by the sphere. So we know that total charge Q is equal to NE, and from this I can find the value of N is equal to Q by E. The value of Q is 1.6 into 10 to the power minus 7 divided by the value of E is 1.6 into 10 to the power minus 19. So 1.6 will get cancelled and here we will get 10 to the power plus 12. So that is the number of electrons lost by the sphere, and when it loses the electron, the sphere becomes positively charged. So that is why in this case the sphere is positively charged. So hope you understood the applications of that derivation what we have derived. So important derivation, very easy numerical, and there are two more applications are there based on the Gauss theorem, so which I will be explaining in my next class. Thank you.